So I'm a chemistry professor, okay, and I do chemistry research, and I'm not going to talk about that today. I also, on the side, some people might say dabble in trying to think about the foundations of physics, and I actually have a couple of papers that I'm working on right now, related to spooky action at a distance. So it's sort of an avocation, but it's also a very serious interest of mine, and it's, in my opinion, far more interesting than my chemistry research. But it's not what I do for a living, okay? But at some point, at some time you reach a point where you don't worry about what you do for a living. You just try to do what you want to do, and don't worry about, as long as you keep getting paid, you don't worry about whether people think you're, dabbling around in stuff you shouldn't be messing around in. So I'm a chemistry professor. I'm a physical chemistry professor, and I've always been interested in the foundations of physics. And so I don't know how much you know about, modern physics. Probably most of you know a little bit and don't know a great deal. So let me just try to keep things, as basic as I can. And by all means, pop in with questions as we go along, okay? Because I don't really have, anything prepared to say except sort of in a general sense in my mind. I have a pad of paper here to write on too if you need a pad of paper. Okay? But this is going to be very, very informal. And modern physics goes back to the scientific revolution of Copernicus, Galileo, Kepler, and Newton. And that established what is known as Newtonian mechanics, or classical physics. And that stood the test of time, including incorporating electric and magnetic properties into physics. Okay, so stuff involving light at the end of the 19th century. And then it became apparent that there were serious conflicts with classical Newtonian physics and electromagnetic theory. And it also was becoming clear at the end of the 19th century that people needed to understand the atomic structure of matter. Okay? And so two great, or maybe three great developments in physics took place in the first quarter of the 20th century. And one of those is a theory called the special theory of relativity, which was due to Lorentz and Poincaré, and probably more than anybody else, Einstein, in 1905. And the second theory was called the general theory of relativity, which was mostly, due to Einstein with some, help, from other people. But basically, it was his creation. It was a theory of gravity in 1915. And then the third theory was quantum mechanics, which was more or less figured out by 1925, 1926, with some, additional, major touches, after that. And so I'm not going to talk about general relativity too much today. Let me say a bit about Einstein and his social views, since somebody mentioned that, okay? And so we don't, forget to mention it as time goes on here. So Einstein was always interested in social issues, and Einstein was kind of a nonconformist. He left Germany, where he was born, to finish high school in Switzerland, and he didn't get along with the authorities very well. And in World War I, which started in 1914, Einstein was just totally appalled by the whole business, and called himself a pacifist then. And in retrospect, it's too bad that the world's leaders were, not as wise as Einstein, was then, because there was this pretty much senseless slaughter where 10 million or so people got killed, and the Russian Revolution came along, and partly as a result of the war, and many more million people got killed. And so Einstein was a pacifist, but as Hitler came to power in Germany, he changed from being a complete pacifist and actually thought that it was essential to rearm and fight Hitler. And again, if the world's leaders had been as far-seeing as Einstein, and if they could have persuaded the people they were leading, maybe that horrendous catastrophe could have been avoided too. Einstein also was instrumental in the development of the atomic bomb. And when it was finally used on Japan near the end of the war, or actually it was the end of the war, but the Germans, the Nazis had already surrendered. Einstein was appalled by that too. So Einstein's views on political things, and especially issues of war and peace, were modified quite a bit over time with developments that were taking place. And it's very interesting to read about them. People often say that Einstein was a very naive guy, okay, when it came to political affairs. And in some ways he was, okay. I mean, he thought that people could be reasonable. And of course we know, that's kind of naive. But he wasn't totally naive. I mean, at least in my opinion, on World War I and World War II, at least the need to fight the Nazis, he was, spot on, okay? And then in my opinion, and it's just my opinion, later on his judgment wasn't as good as it had been, before. So Einstein was accused of, sometimes of being a fellow traveler with the Soviet Union, which I don't think was not true, and I don't think was fair. And he certainly was. He was an American citizen by that time. He moved, to escape the Nazis in around 1930, 31, something like that. And he considered himself very much, at home in the United States more than any place else that he had lived. And there's even a story that the judge who swore him in as a new citizen, as a naturalized citizen, had a big picnic for everybody that he had naturalized. And Einstein, who was quite old at the time, took his whole family, quite a ways to go to this picnic. So his American citizenship meant, a lot to him. But in my opinion, he was somewhat naive about the Soviet Union. But that's just my opinion. If you want to read about Einstein, there's a wonderful biography by a guy named Walter Isaacson, who's written other books, Isaacson, that came out a few years ago, and I strongly recommend that biography of Einstein, if you want to read a biography. And then there's also a book called Ideas and Opinions, which is a collection of Einstein's writings over the years on social and other matters, and also scientific matters. So Ideas and Opinions, and I recommend that if you want to read some stuff that Einstein wrote. And if you want these references from me, just email me, Kellman@uoregon.edu, and I'd be happy to give them to you. There's also a book that we're using in our class on relativity, which I recommend if you want to learn about relativity. Well, so anyway, enough about Einstein's social views and views on war and peace. We're here to talk about spooky action at a distance. So the deal in special relativity is that it leads to a very profound reconception of the idea of time from the Newtonian conception of time. The Newtonian conception of time was of absolute, by the way, any questions about what we've been talking about so far? I don't want to just sit here and talk the whole time.
What class do you teach?
So I'm teaching an honors college colloquium called Relativity, the Quantum, and Reality. I forgot to mention that. Yeah. So that's the class that I'm teaching this quarter right now. I did it last year, and I'm doing it again, this year. And then in the future, who knows? But so I've been interested in these scientific matters, and I decided, partly because our dean, David Frank, finally persuaded me to teach a course, and also other people like Louise Bishop and her husband Jim Earl. Jim Earl was always kind of trying to coax me into doing something, and finally I said, okay, if I can teach what I want to teach, I'll do it. And I said, this is what I'd like to do, and they said fine. So I've been doing it. So relativity involves a reconception of the idea of time, and the Newtonian idea of time is that there's absolute time. And what that means is that the time is the same everywhere. Everything that exists, seems to exist at one instant of time. And that's the same instant of time everywhere. And then time flows. So what is existing at the present is always changing. Okay, so there's this strange property of existence that things are only existing really for an instant, and then they seem to pass out of existence, and then a new time comes into existence. And so, apparently we can't, go back in the past and revisit the things that were real, like 2 minutes ago, 2 decades ago, whatever. Very strange property of time that nobody really understands. But what did seem apparent, certainly to Newton, and to me it always seemed kind of obvious, is that there's one time everywhere, and that is absolute time. Newton also had the idea of absolute space, so he had the ideas of absolute space and time. And why he had an idea of absolute space, we probably shouldn't go into too much, okay? But I'll just say a few words about it. It came about because Newton's laws of motion, there are 3 of them, and the second one is force equals mass times acceleration. Okay, well that's fine, force equals mass times acceleration. But then the question is, acceleration relative to what, okay? And if you want to drive your physics, teacher, crazy, you can ask, well, acceleration relative to what? And my high school physics teacher was wise enough that when the wise guys like me asked acceleration relative to what, he said, Kellman, we don't think about those things too much, at this level. We just do the homework problems, okay? And he said, we know what acceleration is. We can feel it, okay, like when you're accelerating in a car, and we don't worry too much about, questions like that. And so, it's not even entirely clear that question has been completely solved. But so Newton had the notion of absolute space and absolute time. And then in this idea of absolute space, there was the idea of what are called inertial frames, which really goes back to Galileo. And what that says is that if you're in unaccelerated motion, so we're in unaccelerated motion supposedly, right here, at least as far as we can tell, sitting in this room, the laws of physics are the same in any other frame which is moving at constant velocity relative to the inertial frame that we're in. So, for example, the laws of physics on a ship that is moving at a constant velocity are the same as the laws of physics sitting in this room here. Okay, so if I have a teacup and I drop the teacup, it falls straight down and breaks. Okay, both here and on the ship. It doesn't on the ship, go in some curved trajectory or something like that. So that's the principle of inertia, that all so-called inertial frames, unaccelerated frames, moving relative to each other, the laws of physics are the same in each of them.
Right.
Does that make sense?
So that's why your cup doesn't spill in your car until you switch to.
That's right, yeah. Then you're in an accelerated frame, and then the cup can go flying through the air or something like that. So, all bets are off when you're in an accelerated frame. The behavior changes. And again, it's somewhat of a mystery why the accelerated frames behave that way. Because again, the question is accelerated relative to what?
Right, because if you're standing outside the car, and the car's going past you, and you're watching the car drop, it's not going straight down, it's going, some sort of curved line.
Going in a curved trajectory, that's right, okay, and so the question is
Is it relative to what?
Relative to what, yeah. And so the idea of the inertial frame and the principle of inertia, or the principle of relativity in an inertial frame, is that all inertial frames, the laws of physics are the same in all inertial frames. Does that make sense to everybody? It's a pretty simple notion, but it took, like thousands of years for people to discover it. Galileo basically was the biggest person, in the discovery of that. But it's very simple, and it seems pretty obvious once you think about it. And the idea of absolute time seems pretty obvious too, doesn't it? Or not, I don't know, maybe it doesn't seem obvious. What do you think? Yeah.
I guess I don't, I'll see what you're gonna say next, but like, I'm confused about arguments about time. It's not a real thing, or like, I don't think of it as a real thing.
You don't think of time as a real thing?
It's not like, it's like a thing that it's like a measuring tool that we've created to measure like, basically like motion or like events.
Although when you call it a measuring tool, what do we use a ruler for? It's
Right.
measuring.
Space. I also think of like, I mean, this might sound crazy, but like, I think of space as like not really a real thing either. It's also just a tool.
Uh-huh.
So it seems like weird to argue about what time really is if it's not even real. Like it can be whatever we define it as, if that makes any sense.
Okay. What do other people
I
think?
mean, you could set your watch to any time you wanted, but if you were trying to meet someone, that would be helpful. Like, we all, like, if you want to say time is imaginary, that's okay, but we're all having an experience together, and is what we're experiencing time, right? Because it's a shared experience, much like space. I can agree that you are this far away from me. You know, there are some realities surrounding it, or at least symptomatic of it.
I agree with what you're thinking at though. It's just like life moving forward. Because time isn't you can set your clock to whatever time you want it to be, and that's just a number. But time itself is more than a number or a measuring tool. It's the progression of life and space.
I thought I once heard that you can measure time as the amount of entropy in the world. So like when you burn a piece of paper, you can't recreate that piece of paper again. So you're at some point forward in time where that does not exist and will never exist again.
Yeah, so some people think that what's called the arrow of time, that time flows forward, is connected with thermodynamics. You mentioned entropy. I don't know if I buy that at all. Okay, I mean personally,
Same here.
yeah. Okay, it seems to me that it's to me that time is more fundamental than entropy.
Yeah.
But that's a whole other that's a whole other discussion and conversation. Let me ask you this. So if you say space and time are tools, I would maybe say that the measuring rods and the clocks are tools that we use to measure space and time, but that space and time themselves have some sort of reality. Can you conceive of living not in time?
I guess what I mean is like, okay, like if, like in our general, like popular conception of being able to stop time, like what happens when you stop time? Like all motion
Right.
stops.
Yeah.
But like, does the time really stop? Because like everything still exists, so I would say that's still like a moment in time, but there's no more motion.
There's no more motion,
So like I think
yeah.
of time as like, more like the way that we conceive of like motion and how it progresses, if that makes sense.
So are you talking from the viewpoint that instead of, as we discussed earlier, just sort of this, we're going forward, things have happened in the past, lots of stuff hasn't happened yet in the future, it's all very, timey-wimey, lovely, whatever, like Dr. Who says. Anyway, there's the conventional, things are going forward and they're happening and they haven't happened yet and then they happened and it's unchangeable versus the whole, like time exists. Everything that will happen is there, it just all exists at once, but we experience it in a linear fashion. Is that what you mean?
I
When you
don't know
say
if I
if
know
you
what you mean.
stop time, time still exists because it's all there?
Yeah, I guess so.
I feel like,
So Einstein, often said that he believed that time was just an illusion. And I have no idea what he meant by that. Or I can speculate, but I don't know what Einstein meant by that when he said that time is just an illusion. We'll get back to what you said in a little while. And I'm watching the time because
Even though it doesn't exist?
even though it doesn't exist, I'm using the measuring device so that we cover everything that I plan to cover today and get to spooky action at a distance. So, in relativity, it was found that it's a very good thing to reconceive the notion of time, and the reason is that electromagnetic things, that is, things involving light, behave very strangely, it turns out, according to experiments. So, for example, if I have a flashlight and I shine the light, light moves at a constant velocity, 186,000 miles per second, in all directions in our space here, at least in a vacuum, okay? Now, if I fire a bullet, so I have a flashlight and I have, shining light, say, in this direction, and then I fire a bullet in this direction, and the bullet is going at point, say, 999999 of the speed of light. The relative speed of the light beam and the bullet is the difference of those, and so it's 0.000001 of the speed of light. Okay, does that make sense? So the bullet is chasing the light beam. The bullet's going almost as fast as the light, and the difference is 0.000001 of the speed of light. Now that just seems to be common sense, okay? And Newtonian mechanics says that. What isn't common sense is that if you can get into the inertial frame, that is a frame moving at constant velocity, the frame of the bullet, okay, so you're moving along with the bullet at 0.999999 of the speed of light, and you measure the speed of that light beam in that moving frame, what you find is the speed of light is not 0.000001 c. C is the speed of light. It's c. It's the speed of light. Does everybody see what the problem is there? In our frame, it looks like the difference is 0.0000 of the speed of light. But if you're riding the bullet, what you see is the light is going at the same speed, c. Yeah.
Right.
Yes. And this is an experimental fact. It defies common sense, but you can do experiments like this, and this is the way things really work.
The problem is similar to if you've got, you're riding a race car, right? And there's one race car going faster than the race car you're in. So the speed, the difference of speed between those, and that's going to be, what that difference is opposed to somebody who's standing by the side of the track, watching the two cars go by, which is, the speed of that one race car isn't going to be, that difference between the two race cars is going to be, different. But it's not going to be the same difference between those two race cars and between the person on the track watching the fastest race car go by. But the problem here, it sounds like, is that regardless of where you are, if you're riding a bullet or you're just standing there, the speed of light
It's the same.
is the same.
Yeah. And that seems impossible. That really defies common sense.
Yeah.
And so Einstein and others, thought about this a lot. Lorentz and Poincaré thought about it before Einstein did. And Einstein's solution to the problem was a lot different than what they came up with. It was that there's a reconception of the idea of time that is going on here. So what Einstein said is that, okay, I have a clock here that's beating at it's going at 1 second per second, okay? If I have a moving clock, that moving clock that's moving past me will be going slower than my clock at rest here on my knee. Okay? This is a consequence of the equations of relativity that Einstein came up with. How he came to this conclusion is very interesting. We're going to get to that Monday in our class. Okay, it's very ingenious how Einstein came up with these conclusions, and we can't go into that today. But that raises a problem. Okay, so if a clock going past me is going slower relative to my clocks at rest relative to me. Well, what do things look like? So imagine we have a bullet, with a clock on it. And the clock on that bullet is going very, very slow because the bullet's going very, very fast. Well, how does my clock look to somebody riding on the bullet? So you would think that my clock should be faster, okay? But the principle of relativity, which we're still trying to have apply in this strange situation, says that all inertial frames are equivalent to each other. So the laws of physics should be the same in all inertial frames. And that means if the moving clock to me looks like the clock is going slower, well, then somebody writing on that bullet sees me going past in the opposite direction, okay? And so my clock should look slower to the person writing the bullet, at least if the principle of relativity holds true. So what do you think it is? Actually, both the moving clocks appear to be going slower. And that's a puzzler to figure out how that can fit into the theory, okay? But it does. It can be fit into the theory, and it does fit into the theory. Another thing in the theory is that a measuring rod that is moving past me will contract, okay? So not only do clocks go slower, but measuring rods contract. So, instead of being almost a foot, this, as it goes whizzing by, will contract, okay? And by the same token, somebody riding on this thing, seeing me go past, will see that my measuring rods have contracted. And again, you have the paradox that it's hard to see how both, measuring rods can be contracted, but they are.
Is that just visually, presumably because of the light, or?
So I would not say that it's just visually. It's not an optical illusion by any means, okay?
But the paper, like the rulers are actually getting shorter.
It actually is.
Really?
Yes, yes.
Yeah, I have like a similar question. So is it the time moves slower and space is contracted just like from the point of view of an outside observer, or like if you're in that frame?
So if you're in the moving frame, everything looks normal to you. So everybody's frame looks okay
To them.
to them.
But to
Yeah.
other people it looks.
The other frames look messed up.
It's
Okay.
like
Okay.
being in a car.
That makes sense.
Yeah. So everybody thinks, oh, my frame is fine. My frame is the true frame, and you're the one who's making mistakes with your measuring rods and clocks. Your measuring rods and clocks are behaving funny. And so everybody has the same point of view, and it all works out. And it's very ingenious to see how all of this can work out. And to do that, you need to study the equations and really think about them, okay? But I'm just giving you a sort of an overview of some of the strange things that happen. Now, Einstein, in numerous places, talked about this reconception of the idea of time. There was a guy named Immanuel Kant, a philosopher, who had written this book, which is supposedly very difficult to understand. I've never tried to read very much of it, The Critique of Pure Reason. In fact, everything that Kant wrote was difficult to understand. And in The Critique of Pure Reason, Kant talked about the idea of absolute time as being a necessary concept, okay, that is just sort of a self-evident truth that has to be true because we need it to make sense of the world. And I don't know very much about Kant, but Einstein was influenced by reading Kant. And Einstein's point of view was that notions like space and time are not a priori truths that are self-evident, but he said they are free creations of the human mind. And so the people in my class, have to write an essay, and one of the things I want them to look at is this statement that these concepts are free creations of the human mind. That always struck me as being really an astonishing statement. Now you may not think it.
Totally like,
Yeah.
it makes perfect sense.
Perfect sense. Well, does that mean that we can just gaze at our navels and construct any world that we want to, and it will be okay?
No, I guess like going back to the example of like freezing time, so
Mhm.
all motion stops.
Mhm.
All you can say like from your observation is that nothing's moving. Like motion has definitely stopped. That's not up for debate. But depending on how you think about time, you could say time has stopped, or you could say, well, time's still moving.
Mhm.
But like all the objects in it are still like, if that's something that's still up for debate, then I
Mhm.
think that kind of shows that it is just like a mental sort of creation.
Mhm. So Einstein's point of view, I think, is much more palatable to people now than it was 100 years ago, because a lot of strange things have been, discovered, since 100 years ago. It always struck me when I was a little kid, and for some reason when I was a little kid I was interested in Einstein, as well as being interested in Mickey Mantle. Who's heard of Mickey Mantle? Everybody knows him. I don't know. I mean, he was washed up long before most of you were born. But I was interested in Einstein, and I remember reading this and thinking, how can he say something like that? But his point was that the idea of absolute time is not something that is self-evidently true, and in fact, you can come up with a different conception of time, which he did, which works, just as well, although in an astonishing way, but it works just as well as the notion of absolute time. And so he came to the conclusion that we really do create ideas, and then they're not entirely free creations of the human mind, because they have to agree with experiment. So we can't just do navel gazing, okay? And say, oh, gee, there are 10 dimensions of time. Isn't that neat? Well, nobody's found the other 9 dimensions of time, if there are. But so anyway, Einstein came up with a new conception of time in the special theory of relativity. And since it's noon, I think we should go on now to quantum theory. Okay, so quantum theory, we'll skip the general theory of relativity, which had to do with gravity and also the question of acceleration relative to what. But quantum theory was this theory developed between 1900 and about 1926 by a whole host of people, including Planck, Einstein, Bohr, de Broglie, Heisenberg, and Schrödinger were the biggest pioneers in this. And it was a theory of the very small, okay? Relativity is a theory of the very fast and the very large. Quantum theory is the theory of the very small. And quantum theory, in some ways, is even stranger than relativity is, okay? So there are many more popular books now on quantum theory than there are on relativity. What's strange about quantum mechanics? Well, one thing is there's this thing called the Heisenberg uncertainty principle, which says that you can't know simultaneously both the speed and the position of an object. So in Newtonian mechanics, we would say, suppose that this watch is a point, okay? We won't worry about, its extension and its structure. But the motion of the clock is described by, at every instant in time, it has a position and it has a velocity. And so the trajectory of this thing is characterized by the position and the velocity as a function of time, okay? In quantum mechanics, Heisenberg says you can't simultaneously know the position and the velocity of the clock, except within a certain constrained limit, okay? And the limit is that there's something called Planck's constant, such that the bigger, the better you know the position of the particle, the less you know about its speed, and vice versa. And the product of these two uncertainties is constrained by Planck's constant. It's a simple equation. It doesn't really matter what the equation is for our purposes. And so you can't simultaneously measure both the position and the velocity of the particle. Everybody with that? So when quantum mechanics was first discovered, it was discovered in one form by Heisenberg and in another form by Schrödinger, who wrote what looked like a completely different version of the theory, but it gave the same predictions, for example, for the properties of the hydrogen atom. And the problem was people didn't understand what these equations meant at first. And so there were fierce arguments about what quantum mechanics meant. And there were these famous conferences called the Solvay conferences. There were famous ones in 1927 and 1930 in which people had ferocious arguments about the meaning of quantum mechanics. And so there's a famous, or it's now pretty famous, YouTube video, you can find it on the web, a short video of the participants in the Solvay conference of 1927 in Belgium, okay, the Metropole Hotel was where they all stayed, and then somewhere they had this conference center, and it shows everybody going into the conference at the beginning, and everybody's happy and smiling at each other, and looking like they're going to have a great time, and they're excited to be there and everything. And then after one of the sessions is over, the film is of people coming out, and they all look very grim, and they're not talking to each other, and they look very unhappy, and so there was a lot of bitter controversy at this conference. It's clear, and in fact, records were kept of the conference, and now there's a very nice book about exactly what everybody said at the conference and interpreting what they said, and it's very interesting reading. Well, part of the nub of what people disagreed about is this. So I can't measure the position and the velocity of the particle at the same time. Does that mean that the position and the velocity of the particle, the speed of the particle, don't really exist? Does the particle have a position? Does it have a speed? You might say, well, maybe it has one but not the other, but the uncertainty principle says that the product of the uncertainty of these two measurements, delta x times delta p, the uncertainty in x and the uncertainty in p, is equal to Planck's constant, and you can adjust delta x and delta p as long as their product comes out to be equal to Planck's constant. And so you have a choice of what you want to measure. So you can either measure the position or the speed of the particle. And so it doesn't make sense to say, oh, the position really exists, but the velocity doesn't exist, or vice versa. Okay?
So one of the things that I've always puzzled about that, because I can understand how you can measure position without velocity, but I can't understand how you measure velocity without knowing position. I mean, I don't have to, somebody sitting there.
So what you need to do is you need to measure the position here and then the position here, and know how far the thing has traveled in a certain time. And so, yeah, there are going to be uncertainties in the position measurement here and the position measurement here. But if you make the distance that it's traveled long enough, you can cut down on that so that you're getting a better and better measurement of the speed.
It's close, but it's not.
It's not exact, but in principle, you can go to a limit where it is exact, where you have the particle go an infinite distance, and you measure one end and the other. And so it's a limit, okay, in which the speed is precisely known. So actually making these measurements, gets into some delicate considerations, sometimes, of just how you actually measure this stuff, for sure.
Should have paid attention better in calculus.
Well, I don't know if calculus will really help,
okay.
people understand quantum mechanics that well.
Okay.
So Einstein was of the view, I think, that the position and the velocity really existed, that they really exist for the particle. And the fact that we can't measure them maybe says something about the measurement process, but not about the real properties of this object. But Einstein was also very well aware that you can take the view, and this was the view taken by Niels Bohr, that the position and the speed do not really exist independent of the observation. That in some sense, the position that you measure or the speed that you measure come into existence as a result of the interaction of the system with the measuring device or the measurement process.
What if you are the object in motion?
Uh-huh.
I mean, you exist the entire time. Your velocity exists the entire time. You're aware of it.
We'd like to think so, wouldn't we?
Does being the particle in motion, is that part of the measurement or observation process? And
Well-
it doesn't refute anything that you said.
So that brings up an interesting question. Quantum mechanics works perfectly well when we're talking about electrons. Okay, quantum mechanics, these paradoxical things have been shown to exist when you look at objects as large as buckyballs. Buckyballs are these molecules of carbon that have been made in recent decades now. Pretty large molecule. Eventually, people hope to measure quantum properties of things as large as viruses. And then eventually they'd like to put you in the measuring device and measure your quantum properties. And so, at least as far as the theory of quantum mechanics goes, it's very hard to see why there's any division between the small objects that obey quantum mechanics and the larger objects like ourselves that we'd like to think have a reality independent of observations on us. Okay? So Einstein was fond of asking people, do you really think that the moon doesn't exist or the moon isn't out there when we're not looking at it? There's a book by a guy named F. David Peat, P-E-A-T, called Einstein's Moon, which talks about this. So Einstein was of the view that these real properties actually did exist, but that they weren't properly, or they weren't completely incorporated into the mathematical formalism of quantum mechanics, which involves something called the wave function. Okay? So Einstein said, quantum mechanics gives true predictions about measurements. Einstein had no problem with that. And contrary to myth, Einstein certainly was not a disbeliever in the Heisenberg uncertainty principle. He very soon gave up trying to get around the uncertainty principle. But what he said was, quantum mechanics is incomplete. Okay? True as far as it goes, but incomplete. And he thought that there should be a more complete theory than quantum mechanics that would have the properties that he desired. And he spent the last 30 years of his life trying to come up with something. And as far as I know, got absolutely nowhere with it. Okay, so some people said, he wasted the last 30 years of his life to a large extent. To which Einstein said, he said, I believe that I've earned the right to make my own mistakes. That was his view. In many ways, Einstein was a very humble man, so that he also, said stuff like, anybody could have done what I did. He said, I just worked harder at it than other people. I don't think that's true. But he also was, somewhat arrogant, or at least, self-confident enough to say, he said at some point to his entourage, which consisted of his wife, his sister, and his secretary, they all lived in this house together in Princeton, that he said, I think it'll take 100 years for people to understand what I'm trying to say, okay? And I don't know when he made that statement. I haven't been able to track it down. It's probably between 1935 and 1955, something like that. So, I think that now people do understand a lot better what Einstein was trying to say. I don't think it took 100 years, but it certainly took some time. And that, brings us to spooky action at a distance, okay? And so Einstein said, and we're going to read this in our class, that left it open whether for the single particle the position and the momentum really exist independent of observation, or whether they come into existence as a result of the observation. He thought that both were reasonable possibilities. But then what he said was, let's take two subsystems which have interacted with each other, and then they separate, and let's do measurements on this subsystem and this subsystem. Okay? So the subsystem, one way you can think of this is two electron spins. Okay? So you may not know what electron spin is. Just think of spin as being like this, or it can be like this. It can be up or down. For electrons, it turns out it can only be up or down. Okay? Now, Einstein's argument is this. Let's prepare two electrons in a state of total spin called S equals 0. How can total spin be S equals 0? Well, if they fly apart and both of them are spin up, then that's not S equals 0. That's S equals 1. It's actually 1. Why is that? Because the spin of the electron is 1/2. Quantum mechanical complication that you don't need to worry about. It's not 1. It's 1/2. So they fly apart. They're both spin up. That's not spin equals 0. So that's not what happens. What happens is they fly apart. You do a measurement on one electron, and you find out that it is spin up. And then if you do the measurement on the second electron, you find out that it's spin down. Okay? Does everybody follow? So the total spin is 0. You do a measurement on one electron. If it's up, the other electron has to be down. Or if the first electron is down, the second electron has to be up. And you do these experiments, and you'll find that it always works. The spins are correlated, opposite spins with each other. Is everybody with me there on that? Okay. So Einstein argued like this. Quantum mechanics says, about the spin, maybe, that the value of the spin measurement comes into existence when you do the measurement. Okay? So, again, if you say that the position or the speed of a particle comes into existence when you measure the speed or the position of the particle, by the same token, if you're measuring spin and you say that the spin value comes into existence when you measure it, well, now you have a problem. And here's what the problem is. Einstein says, well, how do these two electrons know? How do they know, if this one, turns out to be up, how does this one know to be down? Okay?
Are they observing each other?
Well, okay. So one possibility is that they are what I call PERPs, P-E-R-P-S, pre-existing real properties. Okay? And this was Einstein's view, is that the spin must be pre-existing real properties of the electrons. They really are. One of the electrons really is up all the time, and one of the electrons really is down all the time. And so they are created in this experiment, like this, and then they fly apart, and you're just measuring what was already there at the beginning of the experiment. And this seems, like maybe a reasonable thing to say, that these are pre-existing real properties. What is the alternative to pre-existing real properties? Well, one alternative is that they really don't, know what their spins are when they fly apart from each other. You do a measurement on this electron, and it decides, I'm going to be spin up. And then instantaneously, you can do a measurement on the other electron, and it knows to be spin down. Now this presents a problem with relativity, because for one thing, relativity strongly suggests anyway that the speed of light is an absolute speed limit. But these experiments have been done where you do them in our frame absolutely or almost absolutely simultaneously. So these correlations, whatever they are, if they're being created by the electrons communicating with each other, it's much faster than the speed of light. In fact, it appears to be instantaneous. And Einstein called this telepathy, or spooky action at a distance. He was pretty good at coming up with words. So he said, in his serious writing, he calls it telepathy, and in his letters to people, he calls it spooky action at a distance. He didn't like this spooky action at a distance. Okay? So this brings out what the dilemma is that either these are pre-existing real properties, which are not included in the quantum mechanical description, or in which case quantum mechanics is incomplete, or there really is some kind of telepathy going on. Now, it's worse even than that, and here's what the problem is. We can talk about doing a measurement, and let's say the measurement on this particle causes this particle to acquire its spin, and then it communicates with the other particle and tells it to be spin down. The problem is that which is the first measurement and which is the second measurement, according to relativity, depends on the frame that you're in. So that in one frame, it may be that this measurement is first and this measurement is a little bit later. But in another frame, it's this measurement which is first, according to relativity, and this measurement which is first. And so what is the cause and what is the effect gets really scrambled up there, okay? So which electron is telling the other electron what to do? And so this is why Einstein didn't like spooky action at a distance, because it depends on the notion of a time sequence, and time sequences get mixed up in relativity, okay? And so Einstein wrote a famous paper in 1935 with two other people called Podolsky and Rosen. And unfortunately, Podolsky actually wrote the paper in English, and they were all, you know, Eastern Europeans, okay? And Einstein, when he actually read the paper, it's kind of scandalous. When he actually read the paper after it had been published, he said, "Oh, gee, you know, this isn't very well put." It was Podolsky who had written the paper. So this paper now is enormously influential. People finally came around to seeing what Einstein was getting at. And it's also, Einstein, Podolsky, Rosen, the so-called EPR correlations are important in something called quantum computing, which has become a big, you know, goal in technology today. I don't know if it'll ever actually work. But so this paper of Einstein, Podolsky, and Rosen is recognized as being very important now. Well, to finish up today, so Einstein said, it's reasonable to think that there must be pre-existing real properties and that quantum mechanics is incomplete. Because without pre-existing real properties, we have this telepathy, and you know, this just doesn't seem right. Well, later on, there was a guy named John Bell. So Einstein, Podolsky, Rosen was 1935. Einstein rewrote his argument, certainly in a major rewrite in 1949 and another one in 1954, the year before he died. John Bell was one of the few people who took Einstein seriously. And in 1964, he came up with a paper where he said this: suppose that in our spin measurement, see, in this spin measurement, we're measuring spin in the z direction, that is the vertical direction. So when we're talking about up and down, we're talking about with reference to this direction in space. Now it turns out that if you that you can measure spin in any direction that you want. So if you measure the spin, say, on particle 1 in the z direction, and you measure spin on particle 2 in some other direction, which might be, you know, pointing off like this, it could be any direction, what Bell showed is that any theory which, what he showed was that any theory that gives the same predictions as quantum mechanics does for these measurements where the spin directions are in different directions, any theory that has pre-existing real properties in it will give some experimental predictions that differ from the quantum mechanical predictions. Okay? So Einstein didn't have any way of testing whether pre-existing real properties or spooky action at a distance was what was going on. What Bell showed was that any theory that obeys the predictions of quantum mechanics all the time has to have spooky action at a distance. So Bell had a way of testing whether there's spooky action at a distance or not, or whether you know, there are pre-existing real properties. And the experiments have been done, and at first, the first experiments seemed to agree with Einstein, okay? But later on, the experiments were refined, and the experiments all agree with quantum mechanics. And what that means, according to Bell's theorem, is that spooky action at a distance is real. It's really there, okay? So there is spooky action at a distance. And there's a guy named David Merman, who's a professor at Cornell of physics, who said it was a great misfortune of intellectual history that Einstein didn't live long enough that we could get his reaction to Bell's theorem. So Bell's theorem was 1964, Einstein died in 1955. What Bell said about Einstein's reaction to his theorem is that whatever it was, he would have had something very interesting to say about it. I have my own opinion about what Einstein's reaction, you know, would have been, but I'll just keep that to myself. Okay? No, he would have said, yeah, okay, you know, reality wins. Okay, so I learned from you know, experiment, and so there's something really super interesting going on here that now needs to be explained. I think that's what Einstein would say. Yes?
So spooky action at a distance, if it does exist, if it doesn't exist, and S equals 0, what does that mean to us? Like, so what, does that affect our life? Like the electrons?
Okay, so does it affect our life? And the answer is maybe, maybe not. one thing is this spooky action at a distance can take place across any distance whatsoever. And if every electron in the universe was interacting with every other electron in the universe at the beginning of the Big Bang, that seems to imply that there's some sort of stupendous, it's called entanglement of everything with everything else. Okay? So that things that are going on, billions of light years away are affecting things here right now. Okay? But this effect is such that you can't detect it, actually. So you can't send signals. You can't send signals from another galaxy to here. And if you could, everything would be, totally, just total chaos. We wouldn't have any physics at all, because what was going on here would be being affected by stuff going on in some galaxy that we have no hope of ever observing. So things would just be a total mess. Okay? Now, let me tell you something else about what this entanglement is connected with, and that is, and then I'm going to stop, I think. It's almost 1 o'clock. And I want to leave a little time anyway, if we want to stay. So quantum mechanics says, the uncertainty principle says that trajectory should become very spread out. Okay, so the wave function spreads in time. This is part of the uncertainty principle. And so the upshot of that is that if we observe an asteroid, that asteroid has a perfectly good trajectory that we can observe in time. And that trajectory may be chaotic. It may wander all over the place. But it really has a trajectory that we can observe in time. But if you apply the uncertainty principle to the asteroid and estimate how long should it take before this quantum mechanical spreading takes place and is observable, turns out it's not very long, okay? So there's the question of why do we see a classical world at all, okay? So people, a few decades ago, I think the common view was that the macroscopic objects, the large objects, you don't see quantum mechanics because they're too large. And now what is realized is that, no, you should see the quantum mechanics, even in these large objects, like ourselves. And so the question is why does classical physics work? And if classical physics didn't work, we couldn't make any sense of the world at all. And the answer, I think, is not completely understood, but it has to do with entanglement, okay? So the same thing, or something similar to what's involved in these EPR Bell correlations, as I like to call them, also seems to be involved in making the classical world, okay? So in that sense, you could say that the entanglement and the spooky action at a distance, which is involved in the entanglement, play a huge role in the world, because without them, we would not, the world would be nothing whatsoever like the world that we experience. So there's this tremendous interaction of everything with everything else. So this sort of sounds like woo-woo, talk. But everything really is interacting with everything else in some way. Hi, Niels.
Hi.
So Niels took my course last year, and we're filming this now.
Oh, really?
For those who want to watch this,
Very
maybe it'll be on YouTube or something, and somebody will discover something that they violently disagree with me on here. By the way, some of the things that I've said, not everybody agrees with today, but these are my views, that I presented today. Not too much, but some people would disagree with some of the stuff I said today, but so what? So I would say that this spooky action at a distance is very important in the real world to us, but in kind of an abstract way, okay? So, I don't know if, the average person, watching, a football game in a sports bar, really cares that quantum entanglement is why, football is possible, okay? But I think it probably is, okay? And so some people are tremendously interested in this. And it certainly captured my attention as my, you know, as my scientific life has gone on. So that more and more, and I hope nobody from my department is listening to this. Niels, you're a biochemistry major, right?
Actually, chemistry.
Chemistry major, oh gee, I better watch out, okay, so, anyway, thinking about this stuff has sort of largely taken over my mind in recent years. At the expense maybe of, you know, the stuff that I get paid by my department to do. And there's also a book called The Age of Entanglement, and I can email anybody that wants this reference. The Age of Entanglement by an author named Louisa Gilder, which is about this whole business of entanglement in quantum mechanics. And it tells the story very well, largely in the words of the people who, you know, said the things themselves. Okay.
Thank you, Professor.
Oh,
Thank
you're
you.
welcome. You know, I enjoyed doing this. Do you think this would be a good topic to talk about in a sports bar or, you know, a public lecture? Or,
Sure.
yeah. I did it once in Colorado. I talked about, good grief, in one hour I talked about evolution, string theory, spooky action at a distance, and global warming. That was quite, yeah, it was quite a night.